All in this video, we are going to see about graph cut and energy based method. A common goal in any image segmentation is to group the pixels that look similar. Here also, we are going to divide the image into segments. So, in energy based method, we have two terms. One is region term, another one is boundary term. Region term will encourage the pixel in the same region to have similar appearances. It will make the pixels in the region look same. In case of boundary term, it encourages the nearby pixels to took the same label. So which means we will make the nearby pixels trying to belong to each other. So the total energy can be represented as ER plus EB. ER is energy region term and EB is boundary term, and both of them having separate formulas. On applying those formulas, will get the total energy cost. So this is the graph cut algorithm, the major graph cut algorithm we are going to see now. Here I'm going to represent the entire image as a graph. Okay, I'll show you one graph. I'll show you one image. Assume this is my image, a human being with some tree as a background. Okay, consider this image in your mind. I'm going to divide the image. I want only the human image. I want to remove the background of it. So I want to segment only the human face there. So I will try to convert the image into the graph in such a way that the object, foreground image will have a start node as well as the background image will have a sync node. The node which are in red are object terminal, that is foreground terminal, and the node in blue or background terminal that represents the background of the image. I will start with any other neighbors. So look at here this picture. Look at this picture. I may start at any one point. Okay, let us take this part. Okay, I'm going to take this part and I'm going to fix it as a foreground node. And take any part here, maybe this one. Okay, I'm going to take this part as a foreground one. And next step, what I will do is I will check this point and I'll find a similarity with already taken foreground seed as well as already taken background seed. I will check the similarity. If the similarity is matched with foreground seed means I will connect this node with foreground only. In the next step, I will take a pixel here means I will check the similarity with already taken foreground seed and already taken background seed. If the similarity is high with the background seed means I will connect this node with the background seed in such a way that this graphs are formed. And the gray color node are intermediate one, and you check that intermediate nodes are also connected with each other. So the algorithm here is user will make a pixel, a few pixel as a foreground as well as background. They are known as a seed. A graph is made based on that seed. Remaining pixel will connect to the foreground or background depends on the similarity. And here the neighbor pixels also be linked to each other to keep the region very smoother. After finding so and so, after finding the connectivity, we will cut the graph. Look at the second B part. This image is cut down, and after this cut we will having the result like this. The entire part would be divided, the foreground part alone uh, got as a result. This is known as a graph cut algorithm. Next one is graph cut. Okay, now we are going to say about basic binary segmentation algorithm, that is graph cut. In graph cut, I will not focus on the particular seed. A graph cut starts with the box around the object. I will put a box around the object. The background is guessed from the pixels near the box edges. I'll focus only on the box edges and I'll guess the pixels whether it is belong to a foreground or background. A foreground is guessed from the pixels inside the box. Okay, these guesses will be improved step by step, and that is what shown here. This is the first iteration result. The process is repeated with the better region statistics to identify the segment of that. The next one is directed graph. Directed graph, in the previous graph cut we have seen it is undirected one, but in case of directed edge you could see that is a connectivity direction, right? So arrow mark is mentioned, so it represents the connectivity. Okay, so here we have an image. The image shows that undirected result and directed result. The directed result is much better in segmenting the image than the undirected one. Here you could see somewhat wavy results. Okay, let us see very quickly that how the directed edge results in better means. It will focus on the arrow mark. We'll draw an arrow mark along the boundary, and imagine that You have a image like a black cat sitting on the white wall, means there will be much color change, right? White wall is completely different color and black cat is completely a different color. So we will draw arrow mark along the boundary. We'll draw arrow mark along the boundary indicating that bright to dark or dark to bright. Okay, so if you are taking a boundary here, so this side represents cat and this side represents wall, means I will draw the boundary like either this direction or this direction. Wall to cat means wall is bright color, that is white, and the cat is black, so dark. White, bright to dark represents arrow in this direction, and dark to bright represents arrow in this direction. Next, we will use a particular term called flux. This flux measure how much brightness change across the boundary. How much brightness change across the boundary indicates the weight of the graph. We will assign the weight to each edges. So the strong edges will have more weight. Based on that, we'll build a directed weighted graph. Okay, so the direction represents either dark to bright or bright to dark, as well as the flux will measure how much brightness change. If the brightness change is high, I will assign a weight. So we will find a directed weighted graph as a final result. Then the graph cut algorithm is applied, which shows that the undirected graph with unknown weight is much better than directed graph with weighted results. Okay, so this also results in image segmentation. Next, we are going to focus on priors. Priors, we have two priors, connectivity priors and shape priors. Connectivity priors ensures that segmented foreground is single connected component, and shape prior guide the segmentation using prior knowledge of the object shape. Which means I'll tell you. Previously, we have seen, right, black cat is sitting on the white wall. After segmenting, we ensure that the cat tail, a small part of cat ear, everything will be segmented into a particular same region, means that ensures the connectivity priors. Then shape prior means we know the shape of the cat, right? It is something like oval or ellipse or whatever may be. Okay, so we know the shape of the cat, right? We have to ensure after segmenting that the shape is retained as such. Okay, I'm just telling the example of a cat. It may be of any objects. So if you want to ensure the shape, then shape priors are used. If you want to ensure that all the parts of the objects are in particular segmented image, means the connectivity prior ensures that. Next one is continuous relaxation. So far we have seen only the binary technique. Now we are going to go with continuous one. So in previous cases, we will take the foreground as 0 and background as 1. So instead of taking 0 and 1 as a whole number, I am going to convert the value continuous random value. And if I'm going to take a pixel, means I cannot represent it as either 0 or either 1, right? So I will find the continuous value like 0.1, 0.2 or 0.3, so on so, and I'll fix a threshold. If the threshold is 0.5, means the greater than the pixel value greater than 0.5 connects to foreground, the pixel value is less than 0.5 connects to the background. The next technique is random walker. In random walker technique, so we have a graph, right? So in this graph set, we have a graph with certain nodes. Okay, we'll take the first graph. We'll take the first graph, and this is the source node, this is the background node, okay, or sink node. We only know the initial nodes, source node as well as the sink node, means I will start with a random pixel, maybe take this r, and I will walk through it. I will randomly walk through this direction, or I may randomly walk through another direction. So which one is first reachable would be the final result. If I am taking a random walk in this direction, I may connect to background. If I am taking a random walk in this direction, I may connect to source node. So the first reach node would be the result. So if you take W, if you randomly walk in this direction and if you reach the foreground scene, means it will be connected to foreground. If you take a random walk to in opposite direction and if you reach the background terminal, means it will reach the background. So yeah, how will you ensure the correctness, means I will randomly walk in both the direction. Which one would be shorter will be the first reacher one. So obviously that would be the correct one, right? So in this case, the random walk algorithm works. Then multi-region KV segmentation means I'll take K regions and I'll take one label in each region. I'll remaining all the labels would be zero. Okay, let me tell you in clear way. So I will take K regions. If you have entire image, if you divide the entire image into five regions, means I will take five regions. I will take only one label. I assume that is 1. Okay, I will consider the remaining all the labels. Remaining all labels are 0. Then I will compute the probability of remaining all the labels belong to 0. If the high probability indicates, the 0 will be retained. If there is low probability, means it will be converted to 1 in such a way that the foreground will be separated and background will be separated. Okay, so the next one is uh, geodesic distance methods. In this case, each pixel will be, wait, in this case, each pixel will compute the shortest weighted path to foreground as well as to background. Both each pixel will compute the distance to both foreground as well as the background, and this shortest weight path is known as geodesic distance. So if the pixel is closest to, if the pixel is closest to foreground means I will take it as foreground. Or else if the pixel is closest to background means take it as background. So these are some of the graph cut based image segmentation technique.